G'day, let's get into our second lesson in our unit on hydrocarbons. Today we're looking at using hydrocarbons as fuels, where our lesson objective is to investigate certain properties of hydrocarbons, understand the extraction of alkanes from crude oil via fractional distillation, and describe the uses and pollutions of hydrocarbon combustion. Learning outcomes we're addressing as always just below there. We started this unit last lesson by looking at the homologous series of alkanes, looking at some characteristics that they all share in common. They're all part of this homologous series with the general formula CnH2n plus 2, and we saw similar chemical and physical properties. We saw the similar chemical properties in terms of the kinds of reactions they undergo. Combustion reactions we'll look at a lot more today, and free radical substitution reactions. We're also going to focus a little bit today on the physical properties in these homologous series, how these change as you change the carbon chain. So we can see trends in their physical properties and therefore how we use them as the number of carbons may vary. Let's consider the trend in the melting and boiling point of our straight chain carbons, and there's quite a clear trend here, hopefully we can all see. So we got the temperature on the y-axis there, the number of carbon atoms. We're just considering a straight chain alkane. So no branches, just methane, ethane, propane, butane, etc., etc., etc. We can see a general increase in the boiling point, a nice smooth curve there. As we increase the number of carbons, we increase the boiling point. And we see a general trend in the increase of the melting point. We can see this is a lot more variation that we don't need to be specifically worried about right now, just looking at as the overall trend that as we increase the number of carbons, we increase the melting point. Let's consider why this is. We've talked about the idea of intermolecular forces and intramolecular forces. So we've been looking a lot at intramolecular forces, which are the forces within the molecule. So these are our covalent bonds. The physical properties, the melting and boiling points, are dictated by the intermolecular forces. So these are between the molecules. And a while ago, we introduced three different kinds. We had our hydrogen, our dipole-dipole, and our van der Waals. All depends on the polarity of the molecule. Our hydrocarbons are non-polar molecules. Carbon and hydrogen have very similar electronegativities, so they're essentially non-polar. So we have van der Waals as the intermolecular forces between our alkanes. Alkanes are nonpolar, have van der Waals forces, and these correlate, the strength of these correlate with the amount of electrons. So the more atoms we have, the more electrons, the more instantaneous dipoles that we can have. If you recall that the van der Waals forces is just, all atoms have van der Waals forces, it's just the idea that the random fluctuation of our electron clouds can give instantaneous temporary dipoles as opposed to permanent dipoles in the form of dipole-dipole or hydrogen bonding when we have our polar molecules. So non-polar molecules, temporary fluctuations gives a temporary dipole, which is a van der Waals force, which is a force of interaction. The more electrons, the more we have these forces, therefore the more energy it is to break the bonds. Thus we see these trends in the boiling and melting points. The longer hydrocarbons can also wrap around each other, adding to the observed trends. If you imagine spaghetti, you got spaghetti as it gets longer, it can wrap around more, and that can require more energy to break apart. So we can use these hydrocarbons as fuels as well as other uses, and they can be separated based on the boiling and melting points here, their boiling points more specifically, using something called fractional distillation. So we want some hydrocarbons for some jobs, other hydrocarbons for other jobs. We can separate them through fractional distillation, which we'll look at in just a second. Let's look a bit more detail at where we get these alkanes from. And we get them from crude oil, which last lesson we said it's a complex mixture found beneath the Earth's surface from naturally occurring hydrocarbons from dead organisms exposed to intense heat and pressure beneath the Earth's surface. Crude oil, also called petroleum. I'm sure we would have heard one or two of these phrases before. So we said it's a complex mixture. So in addition to just our alkanes, we have all sorts of hydrocarbons. We contain other aliphatic hydrocarbons and other aromatic hydrocarbons. Two new pieces of vocabulary to introduce. Let's explain what we mean by them. All the hydrocarbons we've been looking at so far are our aliphatic hydrocarbons. These are our simple chains, our simple branches, or our simple cyclic molecules, hydrocarbon molecules more specifically. So these contain carbons and hydrogens joined together in straight chains, branch chains, trains? I think that's meant to say chains, or non-aromatic rings. So hexane, we got 1, 2, 3, 4, 5, 6. Then we've got 2,3-dimethylbutane, so our butane parent chain. We've got a 2 and a 3 methyl off of carbon number 1, 2, carbon number 3. And then we also have our cyclic non-aromatic hydrocarbons. So cyclohexane, where we've got our carbon in a ring like that. One thing to note about the cyclic non-aromatic compounds, especially the cycloalkanes, is if we look at the molecular formula, we got 1, 2, 3, 4, 5, 6 carbons, and we've got 2 hydrogens off of each of these carbon atoms in our sp3 hybridization, thus the sort of shape I've drawn it in to represent that. We've got 2, 4, 6, 8, 10, 12. We've only got C6H12. Our cycloalkanes don't fit our general formula of CnH2n plus 2. Whereas if we consider our 2 isomers, our 2 chain isomers here, we've got C6H 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And if we counted up this one, it would be the same. This does fulfill the formula here. Our cycloalkanes need to lose 2 hydrogens in order to form that cyclic ring. Just something to be aware of. But we don't look too much at cyclic compounds in this course at the moment. So these are the types of hydrocarbons we've been looking at already. Straight chains, branched chains, or non-aromatic. Our aromatic hydrocarbons are different. They contain carbons and hydrogens that are joined together with a sigma bonds and delocalized pi electrons, forming in a circle. These are called arenes. So arenes, they form aryl compounds as opposed to our alkyl compounds over with their aliphatics. The most famous, for lack of a better word, example is benzene. We introduced benzene a couple of lessons ago. Benzene is the molecule that looks like this, conjugating single and double bonds. And we've got this delocalized pi electrons, meaning that the electrons can move around. They're delocalized. We've used the word delocalized in our metallic bonding models. Similar sort of thing, just means they're not localized to a single bond. They can move around. And we can have resonance structures where our benzene molecule can move around like that, one resonance, and then our other resonance, which will have the bonds like that. Now, that neither of these are really the reality. It's constantly moving around. These are just the sort of 2 extremes in 2 resonances. And in actuality, these aren't true single or true double bonds. They're kind of 1.5 bonds, like I said in that video, which I keep referencing. And we can draw this with a circle like that to represent the aromatic nature. So aromatic compounds have these delocalized pi electrons that can move around and form these kinds of resonance structures. So we can have substituted benzenes, methylbenzene, dimethylbenzene. We could have ethylbenzene. And we can specify what kind of benzene it is with similar sort of rules that we had for our other types of carbons. So this has a methyl on carbon number 1, methyl on carbon number 2. This will be 1,2-dimethylbenzene. Dimethylbenzene. We don't go super in depth into aromatic compounds in this course. You've just got to be aware of benzene and the fact that they are different to the aliphatic that we mostly predominantly focus on. So we've got a complex mixture. Why are we talking about this? Because we've got a complex mixture of all these different kinds of hydrocarbons, and we've seen up here that the hydrocarbons are going to have different physical properties based on how many carbons they have, and that's going to give them different uses. So, oil wells extract the crude oil and transport it to an oil refinery to refine it. Fractionating columns separate the hydrocarbon mixture into different fractions of alkanes based on their boiling points, a process called fractional distillation. Distillation is a kind of separation technique that separates mixtures, compounds in a mixture based on their boiling point. So very simply, all it does is it boils it to one of the boiling points of the substance in the mixture, puts it into the gaseous phase, and then recondenses it back down to separate it off. Fractional distillation just has a number of fractions that you can collect, and I got 2 diagrams here. The sort of industrial fractional distillation of crude oil, which looks like this, which is what we're talking about now. But you've also got a sort of more simplified version that you'll see as a laboratory technique. But they are both based on the same concepts, and it's all about using a fractionating column. So in this case, we've got a fractionating column there for our simple glassware, whereas the industrial has this huge fractionating column there. Let's talk about how it works by talking specifically about the fractional distillation of crude oil. So it separates the mixture of hydrocarbons into different fractions based on their boiling point. It does this by having a temperature gradient across the fractionating column. The hydrocarbons that are in the same fraction have similar boiling points. So we can see here, we've got very high temperatures down the bottom, very low temperatures up the top. So we've got a temperature gradient from high to low. Same thing here with our simple glassware. We have the high temperatures down the bottom, low temperatures at the top. So then depending on where their boiling point is, depending on where they go from the gaseous to the liquid phase, we can collect them at different parts. So we just saw the trend where we have our lower molecular mass hydrocarbons. So the less carbons we have, the lower the mass is, the more volatile it is. So the lower the mass, the lower the boiling point will be. So the lower molecular mass hydrocarbons are more volatile, having low boiling points. These are collected towards the top of the column. So if I turn into a liquid, if my boiling point is quite low up here, so we heat up the oil, we're in a gaseous phase travel all the way to the top till, say, we liquefy here, and then the fraction will be collected there. Whereas something with a much higher boiling point will turn into a liquid at a different fraction and be drained off at a different point, therefore separating them based on their boiling points. You can do the same thing here, only you've got to manually collect the fractions. So you have the conical flask collect one fraction. When that's all gone, you trade that out, put another conical flask in, collect the next fraction, etc., etc., on a much smaller scale, obviously. So then conversely to that, our higher molecular mass hydrocarbons are less volatile, have higher boiling points. These are collected towards the bottom of the column. So we collect them in fractions. The fractions sort of are across a range of carbon lengths or carbon amounts or molecular masses, you could even say. So we've got similar boiling points in the similar fractions, and these can be used for similar things. For example, the ones that come off at the bottom with very high molecular masses can be used as lubricating oil, paraffin wax, used to bitumen for asphalt, for roads and paths and that kind of thing. Then we can collect other fractions for fuel oil, diesel oil, kerosene, gasoline, etc., etc. Gas up the very top. This is by no means an exhaustive list. There are lots more fractions than this. This is just a simplified version. However, in general, our lower, shorter chain, more volatile hydrocarbons are the ones that are in more demand and more valuable. These are the ones that are used for fuels and stuff. These are the sort of ones that they want to get. We want to get our hands on more so than the longer ones, such as the gasoline for fuel in very high demand. So there's a process called cracking, which is exactly what it sounds like. You can crack a long hydrocarbon into a shorter one, and therefore you can get more of your shorter chain, more valuable hydrocarbons. It's a thermal decomposition of the hydrocarbon. So thermal decomposition, a decomposition reaction, you take one thing and you make it into more than one thing. Thermal just meaning heat, so using heat to break down a hydrocarbon. Now you've got to do this in an anaerobic conditions. So that means without any oxygen, because if you're heating something up with oxygen, you're just going to get a combustion reaction with the hydrocarbon, which isn't what you want. If you want to get the cracking, it's got to be anaerobic, so without oxygen, a presence of a catalyst, and high temperatures to make that cracking occur. No oxygen means the combustion reaction won't occur. So it's cracked into a smaller alkane, and you also form an alkene as a result of this. So a hydrocarbon with a double bond. Also very useful. We have a lesson on alkenes coming up. Why would the alkene always be produced? Well, it's got to do with the fact that there's a conservation of mass. You can't create or destroy matter. The number of atoms beforehand has to be the same as the number of atoms afterwards. So if I do an example where we show the cracking of octane. Octane, oct meaning 8 carbons, ane meaning it's an alkane, so it's an 8 carbon alkane. I'll just draw it a straight chain like this very simply. 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I can count, good job. Fill in all the hydrogens. So again, it has to be anaerobic. If we did this with oxygen present, it would just combust and we would get our complete combustion or incomplete combustion and the products of that accordingly. So anaerobic, high temperatures and a catalyst to help the reaction occur. So the lower length hydrocarbons are more useful. So cracking would simply be cracking it, and it could crack anywhere really. Let's just say if it's going to crack there and we're going to form a lower chain alkane and a alkene. So the question becomes, why do we form an alkene? And it's simply because we've got to have the same number of atoms before and after. So if we crack this there, we would form, what did I crack it there? We would form, let's say, a 1, 2, 3, 4, 5, a pentane. Do I have room? Yep. 1, 2, 3, 4, 5. A pentane. I won't do all the hydrogens this time, but remember, you always do the hydrogens if you're asked to do. And then in order to have the conservation of mass, it means that we need to have an alkene to make sure that all the matter is conserved. Do I have room here? Hydrogen on the end. Oh, I'm not going to do my hydrogens. I'll just be consistent. So like that. So if I count up all the carbons, we've got C8H18. I know that from my general formula for an alkane. If we count up down here, we've got 1, 2, 3, 4, 5 carbons, 1, 2, 3, so we still got 8 carbons, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the mass is conserved. It's a balanced chemical equation. So we can't form 2 alkanes because they would have to pluck some hydrogens from somewhere, which isn't what is observed. So this is one example of a cracking, but by no means exhaustive. I mean, you could crack it there, you could crack it twice, you could crack it there and there, but you're always going to end up with at least one alkene there as a result. And then these fractions can be collected and used for their more useful, or maybe I'll say more in-demand uses. Yep, so we can form a number of potential products that can be formed from the cracking. So we crack the long hydrocarbon into a shorter one, we form a smaller alkene, which is more in demand for its uses, and also an alkene, which we'll see in a moment, are also very useful compounds. Now let's talk about why these hydrocarbons are so useful. Is because we need to generate electricity and generate energy to sustain the kind of lifestyles we have in terms of, electricity use, in terms of transportation, in terms of generating heat for climate, those kinds of things. So we'll look at some of the uses and how we can use them to harness this heat, but unfortunately there's lots of negative consequences that come from using crude oil because it's a non-renewable fossil fuel. So we looked last time, there's lots of pollutants that are produced, and it's also non-renewable. So once it's used, it's not going to be regenerated in our lifetime, which means there's only a finite amount. Let's look first at the uses. So we said that the combustion reaction is very exothermic. We're going to generate lots of energy that can be harnessed. We can use this energy to generate electricity, to generate heat, whether that's for cooking, whether that's for climate control, whether that's for something else. For transportation, to run all our planes, trains, and automobiles, so on and so forth. But there are limitations. Non-renewable. Once it is used, it is not going to be replenished in our lifetime. It takes a long time for the crude oil to develop. So once it's burnt, that's not going to be replenished, like I say, in our lifetime. They also release a number of pollutants depending on whether we got complete combustion or whether we got incomplete combustion. For complete combustion, we form carbon dioxide and water. Incomplete combustion forms carbon monoxide and water, or carbon and water, as well as the carbon monoxide. Carbon dioxide and carbon monoxide are both pollutants for different reasons. Let's discuss first of all the carbon monoxide. Carbon monoxide, CO, is very, very toxic, and it's also odorless and colorless. So it can be extra dangerous because you might not even realize that you're being poisoned by carbon monoxide as you are being poisoned by it. It's colorless, odorless, there's no way to detect it. So it's very important to have carbon monoxide detectors if you're generating carbon monoxide in an enclosed space where there's potential risk of poison from it, because these can detect it, whereas our sensors are limited. So what it does, it reduces the amount of oxygen that red blood cells can carry around the body. So it binds to a complex called hemoglobin in the blood. Hemoglobin's role is to carry around oxygen found in red blood cells, I believe. It inhibits its function, so it essentially starves our body of oxygen, which is very important for us to live. If you're being poisoned by carbon monoxide, you will just sort of start to feel sleepy and then eventually lose consciousness and then die if you are not removed from the gas source, because it is very fatal because, like I say, it starves our oxygen from blood. Now this is found in lots of things where we got incomplete combustion. Commonly it's found in the car engines where we burn the hydrocarbons. If you think about putting petrol is essentially just a percentage purity of octane. So we burn octane, and if there's incomplete combustion, it can form carbon monoxide. So if this is in an enclosed space like a garage or something like that, there's a risk of poison by carbon monoxide. However, modern cars, scientists have developed a catalytic converter which converts carbon monoxide into carbon dioxide, which won't be poisonous. Modern cars have catalytic converters that oxidize CO into CO2. These also reduce NO, nitrogen oxide. These are a pollutant that we've looked at previously in our inorganic chemistry. It can reduce it from NO to harmless N2 if we think back to our oxides of nitrogen being responsible for the formation of acid rain. So it's cool, it's kind of doing two for the price of one, getting rid of two pollutants. However, it is producing another pollutant in carbon dioxide, but carbon dioxide isn't toxic, at least. We breathe out carbon dioxide. Here's a task. Pause and write an equation representing above reaction in a catalytic converter. I've given you the reaction in words. Can you show that as a balanced chemical reaction? It hopefully looked something like this. Oh, where is it? There it is. Carbon monoxide and nitrogen monoxide gets formed into carbon dioxide by nitrogen. Now it does this via catalysis. That's why it's called a catalytic converter. It's a catalyzed reaction and it gets rid of these two pollutants. However, carbon dioxide is also a pollutant that we need to discuss. It's not toxic, but it's what's called a greenhouse gas. The greenhouse gases are a type of gas. Methane's another one, carbon dioxide, ozone. And what they do is they contribute to what's called the greenhouse effect, where gases trap infrared radiation that keep the Earth warm. This is a very important process. Without this process of the greenhouse effect, there would be literally no life on Earth because the Earth wouldn't be warm enough to sustain it. So what happens is there's a certain amount of greenhouse gases in the atmosphere. So if I draw our blue Earth like that, let's go off the frame. Oop, nearly there. So that happy little chappy down there is the Earth. The Earth has an atmosphere full of gases around it like that. So up here, this happy little chappy is the sun. The sun gives off infrared radiation that radiates through space down to Earth. Now, the infrared radiation, some of it's absorbed by the Earth, but some of it is reflected off. Now, if the greenhouse gases, the atmosphere wasn't there, it would just be reflected off into space, and therefore the surface of the Earth wouldn't warm. However, what the greenhouse gases do is they absorb it and they reflect it back down, and it warms the surface of the Earth, and this allows life to exist. Important process called the greenhouse effect because this is the same thing that happens in a greenhouse. Greenhouses in the garden, they provide sort of an insulation that makes it warmer. However, where it gets bad, very bad, is with the enhanced greenhouse effect. So there's been a huge increase in carbon dioxide emissions from human activity. If we think about all of the fossil fuels we're burning, all of the cars and the transport and the planes and all of these huge sources of combustion reactions with hydrocarbons spewing all this carbon dioxide into the atmosphere, we have greatly thrown the concentration of greenhouse gases out of whack. This has been an equilibrium that was established over millions and millions of years as the Earth was changing, you know? And in the very short time that humans have evolved, and in the very short time that something like, I guess, the Industrial Revolution has occurred, the carbon dioxide emissions and other greenhouse gases has skyrocketed. This causes an enhanced global warming, which is very, very bad. Some people describe it as a climate catastrophe that we are currently facing. And there is a vast, vast, vast majority of scientific consensus that this is occurring, and this is a man-made or a human-caused, I should say, phenomena. So let's think about this. We have a increased amount of CO2. So humans come along, here they are, and we build factories that spew smoke, and we have lots of cars, that's a car, and lots of planes, that's a plane. And we get lots and lots and lots and lots more greenhouse gas emissions, and we get an enhanced greenhouse effect. And what this means is that we're trapping too much heat. too much of the heat is being trapped, because some of the heat would be escaping with the regular greenhouse effect, and some still is, but there's too much that is getting trapped in the atmosphere, and it is warming it up to make the Earth a unhappy, sick Earth. And this is having huge knock-on implications, such as rising sea levels, droughts, heat waves, natural disasters, mass migrations of both humans and animals due to their habitats becoming uninhabitable now because of these changes, because of these changing habitats. And it is an emergency of catastrophic proportions, needs swift and drastic measures to reduce this. Now, this is heating up the Earth by what may seem a very small amount. We're talking, a degree or 2 degrees or 3 degrees, which might not seem on the surface a huge amount. However, this is a very delicate equilibrium that, like I said, has been established over a very, very long time, and just throwing it out by these tiny small amounts of an increase in the average temperature is having these catastrophic effects that we've seen in terms of, huge fires and, unforeseen winters and these mass migrations and these habitats that are changing and these animals that are dying and the sea level that's rising, and then there's less land from the continents, etc., etc., etc. So it is a very real, a very measurable, and a very drastic situation that the Earth is finding itself in due to the increase in carbon dioxide emissions from human activity. Now, there are positive aspects to think in the future. I mean, the scientific research is always developing. There's been huge pushes for a push towards greener energy sources as opposed to non-renewable, but rather renewable energy such as wind, solar, those kinds of things. And in fact, they're becoming more economically feasible and much more popular options. However, it's a slow process made slower by vested interest with other people and corporations and governments. Very, very complex issue. But it's not all doom and gloom. We can be positive and we can foresee a potential out of this situation, but like I say, it does require drastic change. So one way, for example, that environmental scientists can monitor air pollution is through this use of infrared spectroscopy, which all has to do with how molecules and functional groups absorb light in the infrared region. We get characteristic wavelengths when we interpret an infrared spectrum that gives characteristic wavelengths and peaks that help identify what kind of pollutant, what kind of molecule we have. Like I said, depending on the functional group that the molecule will have, it's going to interact with infrared light differently. And then we have very characteristic shapes of these peaks, which might not look like anything at this moment because we haven't looked at it much, but it can very accurately monitor and very quickly monitor the pollutants in the atmosphere. These include oxides of nitrogen and sulfur that we've seen in our inorganic unit, as well as the oxides of carbon we've now introduced, and other volatile organic compounds and ozone. IR spectrums can provide information both about identity and the concentration of pollutants. So this is one of the examples of how this can be monitored. If we can monitor it, we can better manage it. We will look at how to interpret IR spectrums in more detail in a later lesson, because this can also be used in synthetic organic chemistry to help us identify unknowns or to confirm or help confirm the identity of molecules synthesized. All right, final thing for today's lesson, which is a bit of a left turn, something we've got to cover that isn't hugely related to what we're just looking at, but we might as well put it in here, is this idea of solubility. Solubility describes the ability for a substance to dissolve and form a homogeneous solution. We generally describe something as soluble or insoluble, but these are just relative terms. You could imagine soluble and insoluble being two ends of a spectrum, and really the solubility, depending on the chemical properties of our molecules, can lie anywhere in there. So we use terms such as sparingly soluble or slightly soluble, but we can just generalize for now as something being soluble or insoluble. Substances with similar chemical properties dissolve each other, and we rationalize this as a catchy soundbite that says like dissolves like, which means like solvents can dissolve like solutes. Consider straight chain alcohols with a polar head and a non-polar tail. As the non-polar tail increases, we can observe the molecule becoming increasingly less soluble. So if we look here, I have a bunch of alcohols that we're increasing the carbon length as we go down, and we can see the solubility in water. So we're talking about the moles per 100 grams of water at 20 degrees Celsius. So this is what I mean by soluble and insoluble are just relative. You know, we can change temperature, we can change the amount, the volume, and we can make something more or less soluble that way. So we're just sort of generalizing for now. But we can see as the carbon chain increases, we become increasingly less soluble. Methanol, ethanol, propanol, infinitely soluble. Then butanol, 0.11, all the way down to heptanol, 0.0008 moles per 100 grams, which is increasingly less than infinity. So let's show why the like dissolves like is reflected by this data. If I have methanol, I've got 1 carbon to a OH. If I got ethanol, I got 2 carbons, propanol, 3 carbons, butanol, 4 carbons, 1, 2, 3, yep. Pentanol, 1, 2, 3, 4, 5, so on and so forth. Hexanol, 1, 2, 3, 4, 5, 6, all the way down to, let's do like a decanol. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like so. So we've got a very polar group in the alcohol there. We've got a very clear delta positive and delta negative for the oxygen and hydrogen, different electronegativities. And then we've got this non-polar tail. As the non-polar tail becomes more and more longer and a bigger part of the molecule, it becomes a more non-polar molecule. So we're talking about the solubility in water, which is a very polar molecule. Again, we've got a very delta negative and delta positive end of that molecule. So the more polar it is, which is what we saw in our table here, the more soluble it is, the less polar it is. So as we have a much bigger non-polar tail, the less soluble it is. So like things dissolve like things. Polar things get dissolved by polar things, non-polar things get dissolved by non-polar things. Hydrocarbons are non-polar molecules. Similar electronegativity between carbon and hydrogen atoms. So if we're just talking purely about alkanes, we don't even have a polar head. That's literally just the hydrocarbon like that, very non-polar. Similar electronegativities between the carbon and the hydrogen. Therefore, they will dissolve in non-polar solvents. For example, methane will dissolve in hexane, both non-polar. Conversely, polar molecules will dissolve in polar solvents. Something like ammonia will dissolve in water, but non-polar molecules will not dissolve in polar solvents and vice versa. So just a little bit on solubility there to wrap up today's lesson. What have we looked at? We've looked at explaining the use of crude oil as a source of both aliphatic and aromatic hydrocarbons. We've suggested how cracking can be used to obtain more useful alkanes and alkenes of lower molecular mass from hydrocarbon molecules. Described and explained how the combustion reactions of alkanes make them suitable to be used as fuels in industry, in the home and in transport. Recognize the environmental consequence of carbon monoxide, oxides of nitrogen, unburnt hydrocarbons arising from internal combustion engine and their catalytic removal, gases that contribute to enhanced greenhouse effect, and we outlined the use of infrared spectroscopy in monitoring air pollution. Tasks: pause, consolidate, 1 column at a time, work from the bottom up. You beauty. Thanks for your time. We will continue our look at hydrocarbons. Next, we will dive into the alkenes. I look forward to seeing you then. Bye-bye. Have a great day.